Hi all, this is Claudio from expertfea.com with a new stream regarding biomechanics simulations, which contains a vertical shear injury. So at the beginning, let me give you a reminder about what this problem is dealing about. Here we can see it very well. The fracture is on this plane, let's say. And very good to take into account is the fact that this injury occurs when there is a vertical fall. Yes, so it comes, the human body falls from a certain height, pretty high, let's say, in value. It impacts firstly one of the feet, and the shock propagates into the leg bones, let's say, then into the next system, a skeletal system, which is the hip and the pelvis here. So I would say that what we found here is pretty straightforward and easy to understand. So let's not prolong this too much. Here, I think it's another scenario. Yeah, here is two. I hear that two legs, both legs were let's say impacted. Here we can see that the femur caused to break these joints, both femurs. Then the landing was on both feet. It's not our case. Let's not divagate too much. So yes, these two pictures cover everything that we need. A small reminder about how it looks like. So we have here some ligaments besides the femoral joint, which is situated here. Also, let's take into account these ligaments between the spine and the pelvis here. If I click, does it say something? Posterior sacroiliac ligament, all right. And the Sacrotuberous ligament, all right. So these are the ligaments which, let's say, pretty rigidly keep in place this bone with the sacrum, yes, the ilium with the sacrum. So we have the propagation of force of the shock from femur through the iliofemoral ligament, pubofemoral ligament, yes, ischiofemoral ligament, iliofemoral ligament, these ligaments. Of course, we have this joint, which is the main propagator of impact of shock. And here, there's the pelvis, the ilium, let's say, pubis here, and ischium, pubis, and okay. These are pushed upwards by the femur. Then, due to the very, let's say, rigid bonding here, there will be a crack here, yes, and here, exactly as depicting depicted here. Here I think only the ligaments will break, but here also the bone will break. Yes, so let's take this into account. Now, this was the anatomical side, let's say. Let's go with the 3D model. Towards the 3D model. I will, because breakage and fracture will appear, we will need to work, of course, in explicit dynamics. And for geometry, all right. So I took the liberty of editing and optimizing the 3D model. Let's cut it from here and put it here, because this will be the geometry that we will use. Stream '21. Pelvic vertical shear. All right, so let's again assign this, and let's take a look in space claim. Do we have any message from our viewers? For viewers live, hello, welcome. All right, so stream is starting now. So we have seen an overview about the anatomy, about the process, and how the shock propagates into the skeletal system. Let's see if I can zoom in. Okay, I can zoom in. I wanted to see this one. Yes, it's landing on one foot, and it propagates into this joint. And due to a very well fixation here, where possible, it starts to break. So this is the 3D model. It comes from a sitting person. Yes, so imagine the rest of the spine there, and here the feet coming at a 90 degrees angle. It's kind of a mix of shell and solids. And sincerely, I would like to get rid of the shells. These are the shells, yes, with no thickness. And I would like to keep the solid parts. So you can kind of put your hand on such a model from either Piper, Toombs, Adams, and other 3D Hans from ansys, and other, let's say, human body model which exists on the market, let's say. So let's investigate a little. If you see here an enclosed cube, this means surely it will become, after conversion, a free solid. And if you see it open, you can see it has 3 sides. Then surely it will be a shell, a surface body in the end. So let's take a look on, for example, we don't need this. Yes, this is why I hid it, because of what this model has overlapping shell and solids overlapping. But because we're not going to work in shell, yeah, for easier, let's say, approach, normally in explicit dynamics, everyone and everybody works with shell bodies, all right? But for easier understanding and for the purpose of quick stream, we will kind of delete what we have as shell. Let's hit undo a little to see what. Interesting. Where did it disappear? Here. Let's hide the others and try and understand what happens here. It's not very useful. This is why I would like to delete it. Even though we will have something like here. It's kind of open. All right. So I need this to be shell, and you'll understand maybe in a few minutes why I need them to be shell, and here we have the rest is all right. The rest is solids. All right. This is solid. What? We have spongioside, which is inside, and the cortical part of the bone, let's say, which is outside. Do we need to have no, I would like not to have this dissemination between the harder part of the bone and the more brittle part of the bone, because the focus will be on the vertical shearing, not exactly on the bone. And for the purpose of this stream, we welcome having a pretty rigid, let's say, pretty rigid bones. Let's see if I delete this. All right, I have the model. Here, for example, this is shell for sure. This I don't need. These are shell bodies. Here, this will be the cortical part of the bone. Let's see if I delete it, what will happen. Nothing important. So this is the spongioside bone. I don't need this because it is a shell. This is also a shell. And then let's select with Shift and delete. All right. Very nice. Sacrotuberous towards, all right. Let's take into account the fact that we need the ligaments, yes? Let's not delete everything that comes by. This would have been nice as a ligament, but this ligament envelops the femur. I will not leave it because I would like to kind of bond the femur here in this socket. If I leave that ligament as exists here it's clearly is covered, yes? The femoral head is covered by the ligaments. Then maybe some persons, or I don't know, beginners, whatever, they will not understand how the shock propagates. So not everyone is an expert in this type of injury. So let's at least leave something open and understandable for the masses, let's say. So shell, but it is here we have ligaments. Then bone, solid bone, ligament. Here we have a ligament which I would like to delete because we already have the bone. Where were we? I think around here. Sacrospinal, all right. Sacrotuberous. Spongious where? Okay. I will delete these vertebrae. Locating structure 3, delete. Locating structure 3, delete. Because all right. We have done some work, you know. This calls for a save. I would like only to focus on these types of, only on the significant bones, these ones, also this one, and this one. If somehow the FEA will prove too much, we can work only on half symmetry, yes, by having these three. But I would like in the beginning to work with the entire 3D model because it will be more spectacular if everything goes smooth. From experience, I know that this is a shell. Yeah, this one. And I would like to delete it, right-click, show all, and we have everything solid here, except, of course, the ligaments, which at this moment I will leave them as shell bodies. And this, if needed, I will thicken them, I will make them solids. But let's hope they work as they are. So I'm pretty happy with what I have here. Oh, the only thing that we need to do now is to rotate the femurs 90 degrees in order to have a vertical fall, yes? So let's take these three, but I am interested to see the rotation. Normally, this coordinate system should be around here in the socket, yes? So let's hide these. Let's find the same point, if possible, the same vertex. Ah, okay, we can. For example, we'll create a point here in this dimple, and we'll create a point here in this dimple, something here. Between these 2 points, I will create an axis. Come on, can I not select? All right, let's create these two, and the line is perfectly defined by 2 points. Why I created this? Because I'd like this to be the rotational axis for the femurs when I rotate the gum. All right, let's show all. Now we have a proper reference for the rotation. 1, 2, 3, 1, 2, 3 to select solids. Move, and I will click the anchor here, then click the location, all right, which will be the axis. Now I will rotate around this axis, yes? So let's go in the this is the proper vertical orientation of the entire hip, pelvis, whatever. So let's make it somehow vertical. Do right 90 degrees. Let's right 90 degrees, why not? So, of course, you will see some overlapping now. And And let's move them. I would like to move them in tandem if possible. So move how? Something like this, here and here. We don't need to be everything to be perfect here. I think I forgot a bone type here. Yeah, or maybe I made a duplicate, maybe. So we're here. I'm trying to see if I need more. Maybe let's rotate a little inside. Can I rotate a little inside? Let's see. I'm wondering if I will complicate too much or maybe damage what we have now. You know what? Let's leave them like this because I'd like to keep things simple. Yeah, of course that there will be collisions here. So let's go for prepare interference. The collisions are not shown because after all they're faceted bodies or shell bodies or bodies which come from STL or OBG or something like this, all right? So let me show to you what I'm talking about. So these bodies, they're not solid, all right? So let's see if I can make, look here. Oh, this is empty. This is not solid here. When it is solid, a section view will show hatching. A hatching, yes. So because there is no hatching, it's empty inside. I don't like the fact that here is empty. I would have liked pretty solid inside. This means I should have kept the spongious side of the bones or the femurs. But if I would have kept the spongious side, then we would have kept the smaller part of the bone, let's say. You know what? Let's keep in mind the fact that somehow we'll try and solidify here. So we have two types of void. We have a void here due to the STL and OBG provenance, but we also have a clear void here. This void will be solidified pretty soon when we make it solid part, let's say, or body type instead of surface type. And this one inside, we will see how can I solidify it. What I would like to understand is if this concerns me at this moment. Let's do our best to kind of solidify what we have, if possible. With smooth 3D models. Let's see, I don't know if it will be possible. I would like to auto-skin for you to understand. Come on, what are you doing? I would like to auto-skin and to have smooth bodies, not faceted. I don't want to be forced to make such mesh. I would like to make either coarser or a finer mesh. Yeah, this means we need to get rid of the facets here. If possible, we'll do this. If not, we can right-click and convert to solid bodies, which is the quickest way to obtain solid bodies. So here, let's go for version 2, because I will. There is a possibility of kind of ruining what we have, but we can revert from the. We can revert the geometry. We can recover it from the saved file. So, all right. We have here the command autoskin, and we can click here, see what will occur. It says that it has some problems. Let's ignore it for this moment. At this moment, let's try on autoskin this femur. This will work. Okay, with a small error there. Let's repeat the command autoskin. Of course, this here, it will not work because they are kind of mirrored. I can bet they are mirrored, and they keep the same error. So this is smooth solid. Yeah, no facets. This is what we would like to have. All right, let's autoskin this half of the bone. A small problem being the fact that I didn't delete this. Shall I? All right. Let's do the same. Autoskin here. We have like an overlapping faceted body. And now we'll try and hear what we have. For example, this. Let's regard only these two. Come on, I hit delete here. So we have here a big chunk, a big surface missing, and here we have a big surface missing, if you can see it. Firstly, we have repair and we have missing faces. This face is easier to solve, let's say, because it only has around 4 sides, 1, 2, 3, 4. Let's try and heal this face, if possible. It's not possible. Could not replace faces with a single face. All right. Let's hide this and let's focus on this. In order to help with the healing, because it has too many sides, ideal is to have 3 sides or 4 sides, but not more. Just idea. Each extra side or curve will add to the complexity of the patch to be inserted, and this means that it will be very hard to. There will be an interpolation here, and it will be very hard to touch with the new patching face. Yes. Just for fun, I will click here in order for you to see the complexity. You see here the interpolation, how it tries to do it, and it's very weird. Of course, it's very improper. Let's undo here. And what I propose is to delete some of the other faces, if possible. We have this curvature, this, and of course, I think it will not make the proper patch here. It is kind of better, all right, but not perfect. What I would propose is further on to also delete this one. And now, hopefully it will work, hopefully. Yeah, it almost works. Let's go a little more with the simplification. So we have this side, this side, this side, and this side. Let's see if it's enough. Not nearly enough. Can we dare only these two? And you see, it's such a straightforward, empty, such a straightforward void here. So this is kind of done, and it looks very nice. And let's repair this one if possible. I don't know if it is possible. Oh yes. You know what? Let's leave it like this. Now what I can do is show all, and we can repeat the process here, but because we know that the geometry is mirrored, like we would have a perfect mirroring, a perfect symmetry of the human body, which of course it's not the case. So what I would like to suggest is to take 3 points from this plane, 1, 2, 3, preferably not collinear. These 3 points can be perfectly defined. They are enough to define a plane. And here we will, referencing this plane, we will mirror this part of the sacrum, yes. So my formation is as a mechanical engineer, so my anatomy, it can be sloppy sometimes, so I apologize. So mirror, let's select the plane, now the body, and I would like to merge mirrored objects. I don't want mirror relationships. Merge mirrored objects. Hopefully now we have one body, 1, 2, 3. 1, 2, 3, not so much one. But let's see, if possible, with combine, let's see if we can join them. With control pressed, let's see if we can obtain one body. No, not so much. Just for fun, if we hit here interference, there are no interfering bodies, even though I know that these two, look here, they interfere. All right, let's consider later with these two. Now we have these two bodies, which in the past we have seen that they had some problems. Let me show them. When we're talking and dealing with STL, OBG, faceted bodies, we're working with the facet stub, all right? So the problems were here. These were the problems. We had fix sharps. Fix what? We have sharp edges. And another command is to fix them, all right? So let's click here, check. And now when going for tools, auto skin, normally it should solidify them. Let's see if it is the case. Yes. Perfect. Right click show all, and we're approaching what we want. We don't need faceted bodies. And step by step, we're approaching what we clearly wanted in the beginning. Let me also solidify this, which is clearly called pubic symphysis. All right, and it's pretty easy. I think to auto skin them. Yeah, if they didn't have errors. But they have errors. No problem. Right click, hide others, and we're going here for facets. It will show the problems. You can see that the geometry is not perfectly symmetric because we have different errors. If it were a perfect symmetry, then we would have had the same errors on the symmetrical identical parts, let's say. So let's obtain 3D models here, because this one has a problem, and I think it cannot be easily solved. This part we will mirror it as we did in the past. We pretended to have perfect symmetry. So mirror, this is the plane for the reference, and this is the part to be mirrored. I don't care about mirror relationships. All right. So 1, 2, 3, delete. 1, 2, 3, delete. Now everything looks perfect. Let's save. What is this? What do we have here? This is the spongious side of the bone. All right, let's just delete it. For fun, can I rotate a little in order to understand the component, let's say the composition of the bone? Let's look a little something like this. And we're going for section mode here. So you see what I was telling, I don't know, 10 minutes ago. When it is solid, we have a hedge. Here we have something like this. This means we have the inner part, the spongious part of the bone. Yeah. So let's kind of delete it. The easiest way is to hide here and triple click, delete, show all. Look here in section, everything should be solid. We're ready for FEA, or we made the greatest steps towards FEA. Because the FEA will not be done with faceted bodies, with these bodies, we need to see what we can do. Either we auto-skin them and they would remain shell long strands, yes, like ribbons, shell bodies. Either the easiest way is to right-click, convert to solid. Yes, this is the easiest way. Let's do both. Let's do both. And skin surface, for example, look here, we have skin surface here. For example, if I hit auto skin, what would happen? I'm curious. Could not generate cut surfaces because I think it intends to make them solid. But let's hit skin surface if possible. It's talking about a cut surface. All right. So yeah, let's say it doesn't work. Why? Because it's not even close to having a solid. It's very wide open. Yes. In order of each software, in order for it to extrapolate and try to enclose an open body, I think it needs at least maybe 3 walls. Okay, or I don't know if we're talking about a cube, maybe at least 5 walls or something like this. So let's just do it the easy way. All right. Right click, convert to solid, merge faces. So this will be shell surface bodies. Yes. Let's right click, source, internalize all, save, and file save it as version 3. The problem with right-click convert to solid is that it keeps the facets and it forces the mesh to go through here, but it's not such a big problem. Just for fun, I'd like to see if we have autoscan. We don't have autoscan anymore. These triangles can be removed. We can make them disappear using the virtual topology in the model. Yes. So an open issue remained the fact that we cannot merge these two and these two. Yeah, the sacrum and the pubic symphysis. We cannot merge them, and I'm thinking if it is needed so much to merge them, or if we can make something. I was thinking of something like this. Look here. Design, sketch mode, and we will go here. Here I would like to propose to have if possible, let me create some notes. Is it possible? No, it's not so possible. We have a vertex here, and we have another vertex maybe here, and another vertex maybe here. I would like to have these 3 or 2 maybe vertices because I'd like to create an axis. And I'd like to have this axis for sketch mode. I'd like to use it as a reference here, if possible. Look here. For example, we have this the name the command offset curve. Let's see if we can use it. No, it's not possible. At least let's create a construction line if possible. Is it possible? No. Let's project something onto our sketch. All right, we have projected this line. This is in our sketch. Now let's go for the offset. You'll understand in 1 minute what I want to do. I would like to make like an offset like here, maybe 2.2. Another offset here, again 2.2. I would like to make these 2 lines. Yeah, select them with Control pressed, and I will uncheck here construction, and they will become classic line or field lines. All right, normal lines. Let's attempt to create a rectangle here and here. We'll keep only what we have inside. Now let's go with the trim command, and we will delete what we don't need. We don't need this. So we have this rectangle. With this rectangle, I would like to cut the sacrum. Yeah, this is the rectangle. Let's see, just for fun, if possible, cut here, and I will drag and drop something like this. Of course, it will not work. Let's hide one of the halves of the sacrum. Pull cut. Can we cut at least one? Oh, yes. We can, but not until the end. Ta 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 ta. If I make this like here, can I then cut this half with this part? No, unable to intersect bodies. Yeah, the geometry is too complex here on this side. Can I extend this with, I don't know, maybe 3.5? Also on the other side, 3.5. And now maybe cut. Let's see. Yes. Let's rotate it back to what it was here. And because I don't really care about the other half, yeah, this is the other half. You know what, let's leave it hidden. Let's mirror. Select mirror plane, this, all right. And now what I would like to do is to make like a blend to kind of merge these two if possible. Let's see. We have the blend command, select faces of edges, blah, blah. And maybe we'll be lucky, maybe. It asks for a guide to influence the blend or one curve for the center line. All right. Can I create an axis between these two? And maybe use that axis a little later on? Let's see. So this face and this face blend. Can I click this as a guide or maybe this one? No. One problem is this corner. Let me tell you, this corner. Should I make the rectangle bigger? Yes. Yes, I should make the rectangle bigger. All right. So let's go back again, cut. In principle, it still stays this corner. This corner impedes the blending command. For fun, we have a so-called split command. Click on a face to be split. No, a split body, I wanted to say. This is the target. I would like to split by here and maybe to get rid, if possible, if we can get rid of this small corner. No, it's not possible. No problem. All right. So, any remark or suggestion from our streamers, from our viewers? Hello, Shifu, long time no see. Hello. Hi. Shifu, I think it's Chinese. Anyhow. I wish you all the best in your work. Oh, thank you much. Can you mention about AI technologies for FEA? AI technologies to enforce on the FEA. So, ansys AI is implemented now. Just look on Google, it's pretty clearly shown. At this moment, I would suggest to use AI on the research, only on the research or the first part of the simulation. When it will mature enough, yes. And you have seen that ansys AI is already available, and yes, but you know the saying, let it cook. This is the saying. I don't like the rotation here. Can I rotate about this axis? Yes. What? It does not move the anchor. I'd like to use as an anchor this axis. Can I rotate this plane about this axis? I don't know why I kind of lost here. No problem. Let's do it like this. All right, this is the proper symmetry plane. All right. So, mirror. Let's mirror this part. No mirror relationships. Can I create a blend between these two? The problem is that we have here these portions which are not very suitable for mirror. So we attempt again the blend command and it does not work. Attempt blend fails. Does it work with ruled segments and I don't know. Does it work? Do we have the axis? Oh, we lost the axis. Let's rotate the axis. Let's select again these two faces, pretend to make a blend, which will not be possible, and maybe click here, ruled segments. Let's see. Bad profile selection, or they're creating improper intersections. All right. What about if we click this or this? Select guide curves. Of course, it will not work. What do we do? What do we do? Yeah. Can I dare to hope to extrude this face onto this plane? I don't think I can dare because the face is not perfectly, let's say, planar. Look here, it's kind of chipped away. It's broken. But, you know, we try. Let's save it. Up to display. Can we hope? Oh, what do you know? It worked. Finally, some good news. So let's mirror this part, and with no mirror relationships, whatever, merge everything. Yes. 1, 2, 3. Whew. Let's hide it and delete what this one. Finally. Whew. Here, can I merge them? It is a one body. Come on, we have everything. Perfect. Let's go towards simulation now. What I would like to have, maybe I was thinking about extending these to meet these nodes, maybe. Let's see if it is possible. Just asking for a friend of mine. Is it possible? Ooh, this would be nice. Only it damages some of the triangles. Look here. Can we work with these? I don't know if we can work with these. All right, we will prolong, we will extend the pinball radius, let's say. Or I can scale up the sacrum. I can make it bigger. I think I can easily make it bigger because I have enough space here. All right, let's deal with this later. File, save as. V4. And here, let's rename it to V4. Save. Now, let's go here and produce something. I do have saved something like a bone and L. Let's keep this. I don't need steel, of course. And I would like to insert a ligament. The ligament will be a very rigid. Let me tell you what I'm talking about. Ligament. Now, firstly, ligament mechanical properties. All right. they will not give the properties that we like in FEA, so we'll need to kind of extrapolate. You know that the ligament has a rope-like behavior. This means that it cannot be extended. So it's, let's say it has like an infinite stiffness, yes, extending. It's like a rope. And this we'll need to make into account. I will not define it as a rigid body, of course, but we need to think how we were going to supply this rigidity. So let's make this very stiff, maybe 0.1, I don't know. Can I dare to obtain ligament Young's modulus? Let's see if I can dare. 1 and 2 gigapascals. In the range of 100, 300. All right. 100, 300 megapascals. 175. This will impede with bilinear isotropic hardening, which sincerely I don't care. Let's go for ligament density around 1000, or how much? Come on, give us proper density. Oh, yes. Nevertheless, these are in the mouth. Stiffness. They give axial stiffness, let's say. Let's propose kilograms over cubic meters. Knee ligaments 1 to 4 varies widely around. Another study notes that the most density of human patellar tendons. No. Let's go here. Ligament. If it's not rigid enough, we'll maybe change it. This bone might be too soft. We will see it later. So something from the audience? No. All right. Look here, use OVA, yes? So let's go to Claude and ask, when falling from 2 meters high, what reaction force human skeleton body, let's say body, is falling from 2 meters high, what traction force does it experience from the soil of the feet. It needs also, it's regarding the mass. We need to take the mass into account. 70 kilograms per stiff flex. Oh my God. So this means stiff flex, harder floor. This is our yeah, this is the worst case, non-athletic person. 44,000 Newton. This gives us an idea about the force. We'll not go there, maybe 25,000 Newton, but we know what force to apply. Else. The fracture threshold 3,000, 10,000. On the bone direction, yes. So what have we here? The geometry is being imported now. So these are so-called ligaments, and these are called femurs 1 and 2, and this. Sacroiliac, whatever, yes. Ilium and pubis. All right, so ilium and pubis. Ilium and pubis, all right, here and the same. They are kind of fused together. And here we have, this is the sacrum, and this is the pubic symphysis, yes? Yeah. So, can I dare to have written it correctly? With a P, symphysis, is it correct? Ooh, it's perfect. So let's assign bone to bone, of course, no linear bone, and ligament to ligament, all right. The thickness, what should it be? Ligament thickness. Pelvic ligament thickness, if possible. Key measurement include uterosacral ligament, the cardiac ligament, but normally I would like to find out here, for example, it's called iliofemoral ligament. All right, and iliofemoral ligament thickness, how much? 6 to 7 to whatever. Of the thickest part up to 10 millimeters, 15 from the labral edge, thinner region, blah blah. So 5 it is, in principle, 5 millimeters. let's suppress these at this moment. What I'm interested in, I'm interested in seeing if the mesh works. This is an important milestone. Sizing, yes, adaptive sizing. Here 2 for resolution, transition fast, quality, smoothing low. Right click, generate mesh. If I have some doubts is regarding this part, maybe we'll need to suppress it if it gives problem regarding the meshing. Let's see at least if it is meshing something. What I forgot was to resolve the interference here, because we clearly have interferences between these two bones and these two bones. I forgot about resolving them after the conversion from faceted bodies to solid bodies. All right, nice. Let's stop it. Where are we? Here. Double click space claim because I'd like to resolve here the interferences. And somewhere else, maybe here we have interference between these two. Prepare interference. Yeah, this is what I was talking about. And do we click? Yes, resolve. No more interferences. What I'm thinking about, I would have liked maybe to replace that part. So let's go back before the cutout command. Before this command. Let's hide this because I have another suggestion there. And here I would like to cut out this part. This means I will need to make the Boolean operation, the cutout operation manually. The target would be this, and I'd like to cut with this bone. Delete this is the resulting part. I will delete it. Yeah. And let's repeat. This is the target, and I will cut with the femoral head and delete this resulting part. Here, I would like to come up with rectangle, then extrude it to a prism. Let's see if it is possible. Yes. Only should I leave it like this? Yeah. Let's not merge. Something like this is what I wanted. And let's move this here. Let's make it a little bigger for meshing purposes a little later. It merged. It already merged. Come on. I lost it. Come on, stop the command. If we don't click the no merge here, then so we need to click no merge here. It's too late. All right. So no merge. Pull, no merge. I'd like to avoid very small elements here at this edge, at this transition. All right, and let's kind of round all this to make them look nice. Pull, and we're already on the round command. No merge. Oh, it looks so nice. It was a little too much. Why? Because I don't like here to approach too much the bone here. Super. Now let's see, what do we cut? Do we cut the cartilage, the pubic symphysis, or these bones? Let's cut the cartilage, of course. Design, combine. This is the target. We'll cut here. We'll remove the resulting. This is the small pink part. And again, this is the target, and this is the cutter. We will remove the resulting pink small part. All right, so Now in a section view, we can kind of check what we have done. Look here. Is it possible? Yes. Let's see. Look here, the perfect yes. No collision of the hatches, so we have a perfect bonding here. And we can move the plane to also check the pubic symphysis. Look here. This is what we wanted, yes? Perfect hatching. So let me right-click source internalize all, save, and save as version 5 on the drive G. Version 5. All right. So let's keep space claim open at this moment because I would like to update geometry from source in a very quick manner. In the meantime, we're going to look on the chat, silence, which is perfect. So what have we here? The pubic symphysis, which is a bone. Oh, no. Pubic symphysis is a cartilage. It's not a bone. Symphysis mechanical properties. The pubis is a non-synovial cartilaginous joint connecting the anterior pelvic bones, specialized in providing stability, while allowing limited motion to observe shear and tensile stress during working around an single extensive chemical properties include blah blah blah. So I will treat it at this moment. Should I treat it as a ligament or as a bone? Let's treat it as a ligament at this moment, even though it's something in between, I think, or something totally different. Femur. Yes. All right, so let's here click suppress. And I was promising you since a while ago virtual topology. Here I give you virtual topology, behavior medium, right click, generate virtual cells. You see this faceted surface bodies here? Look here, with generate virtual cells, they'll become smooth surface bodies. Kind of smooth. So this software automatically kind of healed and united some surface patches, increasing the possibility of meshing. Yeah, kind of lost everything. It's nice that we saved the version 5 of the geometry. Save often and make backups. Ischium, ilium, ischium, pubis, and ilium. This is the pubic symphysis. All right, then we have sacrum, and here is the coccyx. All right. Where are we here? The project may be corrupted. The project may not open. Do you want to recover the project before opening? Any changes made since the last? Changes made since the last save will be lost. Recover the project. Okay, let's see what it does. So here, let's hit V5. Replace geometry, browse V5. Save. Double click, yes. Now it's importing the V5 version because V5 contained new manually made synthesis. Then we will solve it. We will save it. Save. Yes. You know what? Let's just leave it and duplicate it. This would be like a starting point. What is the time? How many hours do we have? Can I see the time somewhere? 1 hour and a half. We're on the right track, no problem. Double click. So, do we need to pubic symphysis? I said I'll treat it as a ligament, even though it's a cartilage. Let's suppress here and or maybe unsuppress. Let's here click rename based on definition. Let's firstly fight with the meshing because maybe there will be some challenges with the meshing. All right, so let's create again the contacts, taking into account the new geometry cascaded by the virtual topology. Virtual topology kind of created new references and new geometry, let's say. Safe sizing. Use adaptive sizing. Yes, I said here too fast, quality low. Save. I will leave it a few seconds for you to see the values. Right click generate mesh. Oh, yes. We will make these elements bigger, more coarse. Let's focus on the sacrum. What can we do to make the sacrum finer? All these elements are not too coarse for our taste. Let's hit here, I don't know, maybe 10 millimeters. All right, we're approaching something gradually. At this moment, I can say that the sacrum has some problems. The sacrum has some problems. Look here. It tightness. So this means, oh, they look so nice. The ligaments, they look so nice. This means, let's focus a little on the sacrum, all right? Can I go here? Control B and make it, it proposed 1.7, interesting. Let's go here with 3, and for the feature size, let's assign 0.1 heart. Here, there is something here. How many? Around 20,000 nodes. Let's go with 0.01, just asking, just to check. And here 0.25. Uh-huh. 1.5. We can a different approach. Let's duplicate this. And I will say Sacroiliac didn't mesh. Duplicate. We might need to go into space claim and create a wrapping over the sacrum. An offsetted body over the sacrum, you know? We might need to do this because the sacrum, at the point of fusion, exactly on the symmetry plane, it had multiple chipping and small protuberations, holes, and defects, you know, in principle model. So let's, we will see. We can solve it, no problem. Let's firstly try with to know. Usually changes the approach of the mesh, and maybe we're in luck. Maybe. Of course we're in luck, but it worked more. So let's do what I said, because I don't have other ways to heal the geometry inside except the virtual topology, which didn't help too much. Hide others. For example, if I hit here, check geometry, what will it say? Oh, there is an error with the trimming boundary, zoom to fit. Yeah, so you see, it's exactly like the symmetry of the, yeah. How can I heal it? There is a repair here. Do we have a stitch? No. Missing faces, of course not. Split edges, yes, and yeah, we don't care too much, I think. Ooh. No, please, no. Extra edges, duplicates. Curve gives duplicate curves, small curves, merge faces, small faces. Inexact edges, 8 inexact edges. Look here, I don't like too much what's happening. Split edges, duplicate curves, small curves, curve gaps, small faces. Let's try a mesh with these characteristics. This new topology. Let's see if we healed somehow the 3D model. If not, we'll go towards the wrap of the model. The wrapping will cover and ignore all the problems, these small angles and chips and small protrusions, yeah, which they complicate the geometry. Where were we? Virtual topology. Was it remade or not? Let me ensure that it is remade. Let's go here with simplified faces, yes. Delete our virtual entities and let's remake it. Generate virtual cells. So it's simpler now, but let's see if this solves. Suppress, let's go with default. Oh, yes, finally. There is a problem. Where? Some of the elements on the problematic and mid surface meshing was success. Come on. Okay, we don't care. What do you want? Because everything is... the mesh is made. Oh, we didn't delete this body? Locate body in structure tree, go to corresponding bodies in tree. Pubic? What? Pubic. But I have 2 pubics in feces, so let's delete one of those. Show up. Yeah, that one was the problem. So we have a working mesh now. Let's close this because this is nice. We can go towards the FEA now. I'll watch my smartphone for a few seconds. Oh, I have an SMS. Let me take a small break. So we are back now. Let's close space claim. And I said I will duplicate this scenario because we have a proper mesh. Do we have any message or something? No. Which is perfect. Everybody likes peace. This is not properly V5 because I have modified the geometry, optimized it, but let's go with this. Why here is not updated? No problem. What's important is that we have a working mesh now. Let's leave the mesh like this at this moment. Only let's try and force some things. For example, what is this? So I don't care about the contact between bodies because the contact is dealt with this instead of frictionless. It's frictionless inside. It is frictionless, yeah. So I don't want this contact. I would like a contact with the ligament. Only I would like to extend a little. Can I extend a little? Selection. Adjacent? Yeah, it goes. Limits would be nice. All right. And the face. All right. These ones. Let's extend here. Limits apply. Idiom pubis to sacrum. I don't care about the contact between bones. I care about the contact between ligament and bone. Ligament and bone. Limits, extend. Sacrum to ligament, yes. It's not a problem to assign all the entire ligament because only a portion, the periphery, will come into contact. So don't worry about prescribing the entire ligament. For example, here, the ligaments are the blue side, yes. So let's go here. Limits apply. Here, which one is this one? Here, this one. here limits apply. Sacrum to whatever we have. You can see it here. I don't want to zoom in. Again, femur to what we have here, bones and bones. I don't want to deal with bone to bone because it is already dealt. Ligament again. So limit apply. Now, between these two, I would like to leave it bonded. All right. F7. Yeah, the pubic symphysis and the ilium pubis bone. All right. Regarding the ligament, again, limit apply. And again, bonded here. Let's increase. Let's increase this, which is like a pinball radius, maximum offset. Let's make it, I don't know, maybe 1 or something, or 2 or 3 or 5. How much should I make? You know what? 3.5. Everything with the ligament. Let's make it pretty big in order to be found. You know what? I will put here 10. And I will assign non-breakable. Breakable, no. Yes, because we want the high stiffness of the ligament. And maybe the part, for example, here where we want it to crack, maybe the part will crack here. The ligament, and here we want here to crack on this portion. Let's give you a reminder. Yes, so here clearly the ligament breaks. Yeah, near the fixation, and here the bone breaks. So let's see if we can do the same. Let's regenerate the mesh. All right. Now we do have a too good mesh for the femur, which I don't care too much. For example, sizing of the femur, let's make it, I don't know, maybe 7. And the sizing for these bones, let's make it around 6. Right click, generate mesh. I need to just propagate the force. I don't need something else from these femurs. All right. So, how much will the... At a certain point, they said 10 milliseconds, which is 0.01 seconds. Bending is more than 0.1. Let's go with this 0.01 seconds as end time. 0.01. And of course, experience says 1 million -9. These are the time steps, the proposed time steps. Automatic scaling, let's see if it works. I don't know, 6. Here we will need the bones to break. In order for the bones to break, we will need to make here, I don't know, maybe around 0.5. No inertia of eroded material, and here to make the animation smoother, let's say 100 result number of points. All right, as I promised, because when the body falls, there will be near the center of mass, which the center of mass is around the umbilic, yeah, the navel. It's around here. My proposal is to kind of fix the sacrum. Because if we fix the sacrum, we will create the perfect conditions for the shear to appear. Look here how the shear force, shear stress, or how it looks like. Yeah? So we need to have a certain side that is fixed. For example, if we're working with symmetry here, we'll need to fix this side and we will go with this side, all right? Symmetry on the shear force, it's not so correct. What I wanted to understand is that we need to have a fixation plane, let's say, for the shearing to appear. So in order to have this fixation, yeah, we'll need in the beginning to fix. I will not, if it will be needed, I will fix the entire sacrum, but I'm not so desperate. Control F. Let's fix only some of the faces here. Yeah, something like this. Coccyx. So I don't want to fool anyone, but I think we're gradually approaching towards fixing the entire sacrum. All right, so, and if we have a fixed portion, we can achieve fracture. Now the problem that appears is if we will need to fix the pubic symphysis. If the behavior is not what we need, then we will need to fix that, all right? So another thing that will be taken into consideration is that this is the applied, let's apply the force here. Selection adjacent, something like this. And it's about, let's say, plus z-axis, something like this. Let's go to components. I promised something like 25,000 newtons. And because I don't like the orientation, I would like to put a little something on the x-axis. So 7,500. Look here, and now we have an almost axial load referencing to the vertical, or this is the vertical or the axis of the femur. Yes. So now this side stays kind of fixed. So let's go here for box select, and let's kind of fix this side. Can I go for adjacent? Yeah. Let's remove the unneeded faces. This is an unneeded face, and this is a needed face. All right. So what we first here, we will fix on the other side. So we fixed here, we fixed here. All right. Here we have bonded, 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 bonded. What? I lost it. All right. Let's add more faces with control pressed. All right, let's get out of this. And yes, let's apply it. Let's see what will occur. Maybe this is not enough. What I'm talking about is the fact that here in the socket we have a too small area. Maybe we need to have it bigger. This is why the ligaments covered so much went until here, let's say. Yeah. So maybe we needed a bigger area for the femoral head. Let's see what gives. Switch to automatic mode, and regarding the solution, the classical deformation, velocity, stress strain. Save. Yeah, let's see what gives. Three-minute solving, yes, this is promising. We'll need to restrict the movement to the femur to be only axial, maybe. The fact that they pulled only this end is not enough. We need to push the entire bone. As I said, the nonlinear material kind of says to the software that it is pretty soft. What I can see is that we lose the contact with the ligament here, which is very nice for us. Ah, it didn't continue. Okay. This is very nice. We have breakage here. And here it's not so much breakage, but yeah, it's the beginning. So here we lose the breakage, which is nice. We don't have connection with regarding the ligaments here and the bone. We need to increase somehow the pinball radius, but to have this breakage. So this means fixing here, it's very correct, let's say. We lose the connection here with the bones. And I should have kept bonded here and here. So let's do this. Let's better bond the ligaments to the bones and bond the femur with the these bones, yeah, the iliopubis side, okay, pelvis, whatever. This is a nice start, even though I missed some of the joints and proper contacts, but it's a nice start. Do you have any questions from the audience? No, perfect. All right, so I forgot to bond these two bones. The easiest way is to assign a body interaction, Control B, and say something like this. These two bonded, and I would say here, I don't know. Maybe 5 millimeters, breakable, no. Duplicate and assign these two bodies. All right. Now, regarding all these except the 3.5 here, only the ligaments. Max offset, it was not enough here, 10 millimeters. Let's go to 20. Yeah, so it's clearly with nodes from this bone will meet nodes from this ligament, even though they're so far away. Let's see. Let's say. All right, I didn't like the bending of the femur. So I would suggest, if possible, to kind of restrict, to make the bone stiffer somehow. This means I would like to displace this bone only regarding that direction. Let's assign a direction. Because I would like to be consistent with this direction. Yeah. So let's create a coordinate system. We don't care too much because I would select this face, for example. And I will rotate the coordinate system about the y-axis. Look, rotate about the y-axis. I sincerely don't know the direction. Let's make, I don't know if it's positive or negative. Come on, show something. I would have expected to see a rotation. What? Normally, it should rotate, this coordinate system. You know what? Let's select another. Let's select a vertex. Yes. Now, can I rotate? Why don't you rotate? Ah, okay, it rotated. Okay, fine. Ah, I need to kind of refresh it. Okay, and now 25. Yeah, because I would like to select here this coordinate system and select 0 here. All right. Now I have, and this axis again, I will select it here. This coordinate system, both z-axis free, and the rest is 0. Yeah. We'll allow this bone to displace only vertically, because otherwise we'll have that weird bending which we have seen 5 minutes ago. I think 25,000 was too much. Let's solve. So I think we're on the right direction. I mean, the simulation is headed the right way. Three-minute solving. Yes, we agree with this solving. This solving time. Yes, high stress here. This will cause this ligament to rupture. Oh, the FEA just stopped, so it doesn't go anymore. So when fracture or breakage appears, the solver is too much loaded. These ligaments fly away again, and maybe it's time to quit with the shell, with these surface bodies, and make them solid instead. This would be the smartest way. So the FEA stopped. So good trend here. I would have liked here to have also some breakage, but maybe it's not possible due to the fact that these ligaments are not functional at this moment. So let's duplicate and make those shell ligaments. Let's make those solids somehow. Let's see how we can do this. We need to thicken those. It will not be easy because they are kind of faceted. They retain the triangles from the past. There will be a 6th version. In order to have a better realism here, I think I will make the femurs a little bigger in order to better encroach and envelop here in this socket, because now it's kind of it's too small here, and we don't have the proper ligaments now. So my solution is to make this femoral head bigger by increasing the scale of the femur bones, both femur bones. So what I was talking about is something like this. So let's go and hide firstly these two, because I'd like to delete these cutouts, because we'll have newer cutouts. So let's scale these two. I'd like to rotate them a little, just a little. Something like this. Can I rotate a little more? Yes. And we'll go, yeah, it's a little better. I'd like to go here because my intention is to, let's just delete this because I will mirror this one. Let's scale this this femur. Let's scale it. Design pool. Scale about this point. How much? 1.1? Yeah, 1.1. Yeah, it's pretty big, and yeah, it's very nice. If possible, do we get it out a little or not? Let's not get it out. I will mirror it. Mirror according to this plane. No mirror relationships, yes. And now let's make the combine, yes. So I will, this is the target, this is the cutter, and I will remove this pink resulting cutout geometry, combine, target, cutter, and remove this pink cutout geometry. All right. So right click, source, internalize all, file, save as, V6. Very soon. V6. All right. Now As I was saying, I would like to keep only the ligaments. And I would like to somehow thicken them to make solids out of them. I don't know if it's possible. Let's see, Control A. It's not possible. Control A. Can we thicken? We have here thickened surfaces. If possible, symmetrical, pull both sides, but how much? Let's see, 2.5. So for the moment in our FEA, the connection between a shell and solid, between surface body and solid body didn't work very happily. This is why we're trying to use only solid bodies. And I'm trying to thicken these shell ligaments, let's say. Let's see if SpaceClam can do this, the thickening command. There are pretty around 1,000 faces. And yeah, I don't know what it will do. The problem is because they are faceted, the orientation of the triangles will maybe create misproperly aligned triangles, as it did 1 hour or 2 hours ago. You know, I pulled some of one of the ligaments, and it created some weird overlapping surfaces, let's say. Another idea would be maybe to revert them to faceted bodies, because there was a thickening command. I don't like the approach here. What is the distance between this vertex and this vertex? 6 millimeters. Okay, it's acceptable. All right, so let's try something like this. On the facets, if I was to convert, look here. Let's convert them. Yeah, here there was this, I will select them from here. There is this command, thicken. Create a thin closed body from the selected open faceted body. Let's see if it is possible. Click a faceted body. And thickness both inside and outside, and maybe five millimeters, maybe. All right. Fix intersections if possible. Click a body. So. Oh, yes. Yes, yes, yes. I don't like the fact that here it's so... Maybe we will quit before. And here maybe we'll assign 3.5 maybe, yes. Thicken, 3 millimeters maybe. Click a Faceted body. Not worse. What is inside and what is outside? I think inside is the pink. Yeah, it goes there. All right, so we solved it, and it will not overlap. All right. And now it's very easy, I think, to auto-skim them, to make them solids, because they are very, very simple bodies. What do you know? Ooh. Let's save and create a V7. So 96 protrusions, 16 for 1. No, all right. It chopped up a little, but we don't really care. Auto skim, Control A to select all, and this is what we get. So we have 20 ligaments. We only have one solid. What does this mean? Firstly, of course, that the problem is that we have big faces missing. Big faces missing. There are multiple ways to fix this. We can create some wrappings. Let's undo. Let's optimize this. I don't know how to optimize it in a way that takes less work. We have the shrink wrap. Can I get a shrink wrap for multiple bodies? Let's see. Oh, yes, maybe we can. The shrink wrap will automatically create very good faceted bodies outside these bodies that we have now. This is why I would like to use shrink wrap, because the internal, it's very useful. It's very easier for the software to work with shrink wrap bodies. This is a mesh that is not native to SpaceClaim, let's say, but the shrink wrap, it's created by SpaceClaim. It will help with auto skin 1 minute later, you know. Yeah, let's see. You will see more triangles. It will be a finer mesh. Look here. Look here, yes. So it's finer mesh now. Only we have this problem. These fused together. Ctrl Z. This means we need to apply here maybe 0.7 maybe. in order for these two not to fuse together. Yeah, modeling and simulating in biomechanics and using true body parts is not very quick and easy endeavor. So we still have a small fusion here. So now you should understand why there is, at this moment, there is nobody on YouTube and on the internet selling so many biomechanical models as we have. Yeah, so when you see here 78 biomechanical FEA simulations, you need to understand the amount of work and hours of regenerating, healing, solving, realigning, Boolean, intersecting, and contacting. And just imagine for each scenario spending so many hours. It's besides the experience regarding modeling and FEA, we need lots of patience. Lots of patience. You cannot imagine to understand the problem we had when meshing this assembly with the spine, lung, heart, fatty tissue, and even though it looks coarse, you cannot begin to understand what work was input here with irregular geometry as specific to biomechanical parts. So now you have a look inside. So let's go here and check a little. There are no proctors. This means the auto skin should work in principle. Let's see if it does. I don't know why it created one faceted body. I should have expected to have around 20 bodies. I would have expected to have around 20 bodies. Let's see what is the result. Such a fine mesh would surely create a nice solid topology, hopefully. Yeah, it's kind of good. Why is this one body? Why? Let's go a little with undo, and here, if possible, separate all, because I don't like it being one body. Oh, it worked with separate all. All right. You know, when you have a big problem, you need to separate it, divide it into smaller chunks, which are easier to solve and deal with, you know. So, any remark from the camera again flew away. Yeah. Come on. I'll look here to see if they're fused here. Oh, lots of models. Ah, perfect. The only, let's say, remaining problem is here. Let's see how can we solve this. There is this repair command, as you know, missing faces, and maybe it works. Or maybe not. What can I do here to help? Maybe... The problem is that this is the problem. If I enlarge this hole, let's see if it can be solved. Oh, yes, it could be solved. Do I need the facets? No. Right click, show up. Oh, yes, and now we have, look here. We have the proper ligaments properly touching, you see now? What I would like to do is to make the Boolean operation. I don't like here that it's not touching. Let's extend them. At this moment, I don't know how. Firstly, let's scale them because clearly these four clearly not touch. They do not properly touch. They do not unite with the bones. Let's scale them 1.1. Design, pull, scale. I will select this and 1, 2, 3. Let's see. Yeah, I think it's promising. Now we need to just move them a little. I forgot to keep the sacrum. Something like this. Is it touching here? It's kind of touching here. Let's leave it like this. 3.6. All right. So the same. 1, 2, 3. Can I move it? I don't know how. Something like this. 3.6. All right. Even more. 4.2. Even more. 5. 5.5. I'd like to touch here and here. Yeah, something like this, here and here. All right. So this one, 1, 2, 3, something like this, and something like this. Yes. So something like this, and something like this. Okay, here, okay. We have an apparent problem with these two kind of colliding, but in FEA I will define not to interfere. Yeah, we kind of departed a little from the original topology. We are forced by the, how do you say, force majeure. And I will define for these two not to touch at all. You will see how I do it. Yeah, I don't want to solve this at this moment. It's kind of too much and it complicates. It makes things harder to understand to the beginners, let's say. So, yeah. All right. Right-click source internalize all, save, and save as V7, if possible. Can I save as V7? It is possible. All right. Here I will write V7 and double-click model to see if it opens what we have now in space claim. Did the camera fall again? Of course it fell again. Why wouldn't it? Okay. Hey, thanks for this video. It's really helpful for Slimy who is currently exploring this. Yeah, you're welcome. And yeah, be prepared with lots of patience because you need time and experience, and it's not so easy. You don't need to believe me, just see for yourself. It's not so easy. So it just opened here. Let's close space claim. Where are we here? And now we have these. I think they are kind of which one is the femur? Show me the femur. Ah, okay. These are ligaments, all right? So rename all ligament, all right. Ligaments have the mechanical properties of ligament. This is a femur. One, and this is femur, maybe femur two, if hide all other bodies. What is this? Oh, this is, oh, it didn't disappear. This is the pubic symphysis. All right, femur one. Where is the femur? Femur two. All right. No linear bone. Show all. Save. Oh my God, so much work. Let's define. All right, let's quit with the contacts. Body interaction. No more all bodies frictionless contact. Bonded, this one, Control B. This one to this one should be bonded. Also bonded to. to this, 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 to this. All right, we have bonded with ligaments and bonded with femur. Only, I promise you that these two shouldn't collide. So let's exclude the small one. No, let's make it, okay, let's exclude the big one. Apply. Let's do again. Duplicate, Control B, will be this and the big one. And no explicit interaction between these two. They will not interact, especially because I deleted the default frictionless body interaction. Did the camera fail again? Oh my God, oh my God. So let's do the same again. Duplicate, and I would select something like this. This. The small and the other ones. Small, small, small. Ligament. Okay. It's similar to what we have in blue, all right? Apply, and let's duplicate. And let's assign interaction between this one and the long one. And again, there is no clear interaction between these two. Now, let's create, by duplicating, a bonded between this and the rest of the ligaments. This one, this one, this one, this one. Also take into account the same problem, not to overlap those two, yes? Small, small. We'll leave those two at the end. Yes. We will make again this one and the long ones. All right, we solved this, this, and this. Now bonded between the femurs and... but it's already defined. Yes, yes. We kind of defined everything, I think. If something is missing, we can see it during the behavior. Let's delete all virtual entities because we need to remake them. Did I make the proper cutout here? Let's see with the section view. All right, let's generate mesh now. Perfect. This mesh, the sacrum, for the sacrum, a little finer. So So I will exclude it from here. And let's make a sizing of 5. We already have 5. We already have 5 here. Let's see if it's going for 5. I'd like here to have a better joining here. It is kind of better joining here. I need some of the nodes from here, from the ligaments, some of the nodes from the ligaments to find some of the nodes from the bone, from the sacrum. I'm not convinced that we ran an interference command. Oh. What? Let's see let's check for interference and see what occurs. Yeah, I definitely forgot to remove the interferences, the collisions. Due to the complex topology of the geometry, due to the curvatures, the dealing with interference and overall dealing with editing such geometry, yeah, takes much time. They will subtract from the larger body. Aha. Can we subtract from the smaller body? Let's subtract from the smaller body. Do I need the ligaments to be full, integral, or do I need the bones to be full? I would like the ligaments to be very strong. At this moment. Let's run the same command, but we have here this, this collision between these two ligaments. So let's hide these parts. Why doesn't it see here the collision? There is a big collision here. know what? Maybe we will mirror this part, because here is properly colliding and here it's not properly seen by the interference part. Let me delete this and I will mirror this. Let's see upon running the interference command if we have interference here, which should be. Yes, we have the proper interference. So what do we remove? Do we remove from the smaller body or big body? Do we remove from the bone or from the ligament? Let's remove from the smaller body, from the ligament. We will run the same command, but only with the sacrum and the other two ligaments. Sacrum, the other two ligaments, and the big bones here. And let's see what influence we'll have on the mesh further on, because I think new challenges will appear regarding the mesh. All right, so what I wanted to say is let's hide these parts. So let's leave this. Let's hide others. Now let's run the interference command. The interference here is so big that it will not show, but it's not so big. So sincerely, what I would like to have is the same, to have red patches here and here. Here. The software doesn't show the patches from here, from this end. I would like to have also here interference. C'est la vie. Let's work with what we have. On smaller bodies, we will subtract from the ligament. All right. We'll see in FEA what we can do. We'll see. So what we had further on, we had the femurs. Normally it shouldn't be any interference, but let's see. Yeah. What is the pubic symphysis, which gave so many problems in the past? This one. All right, sure. If we don't have all the ligaments, then we will not obtain the proper shearing. This is why I'm struggling so much to have a reliable 3D model. Save. Save here. All right. Right-click source, internalize all, file, save as V8. And here I will call it V8. Let's write here V8 because I'd like to have the proper naming here. All right. Update geometry from source. The camera fell again. This is one of the ligaments. I don't know. Let's see. It says. Okay. All right. Let's remake the virtual topology. And let's there and do we have the proper parts? Oh yes. why do I have bonded here? All right. So what is missing is bonded between this and the ligaments, the sacrum and the ligaments. We have it here. All right. So God help us all regarding the mesh. Because now we have, after interference, the interference command, we have small dimples. Ooh, we're blessed. The geometry worked very nice. What is this? Fixed support on the sacrum, and there was a fixed support here. Oh, I need to remake. All right. It's kind of too much. The annoying cursor. The annoying cursor. Alright, so the force is on the right. I will remake it, of course. And I will fix here. Finally, it's updating correctly. Displacement of, again, this face is, here I will select the entire bone. If needed, I will make these ligaments rigid, if needed, in order to obtain a solution in this stream. Because we are approaching, we're way past 3 hours and we need to keep it short somehow. I started watching your live stream series from the past 2 days. Can you suggest me anything from where I should start? I'm also exploring ansys automation. Do you think there is any scope? Programming and coding is always helpful for experienced users, of course. And it depends on what you want to learn. What is your formation? Yes, either you are new in ansys or you're a mechanical engineer or a bioengineer or medic, or yeah, it kind of depends. So tell me, where are you coming from, and I can point you in the right direction according to my perspective, to my vision. So tell me more. Yes. 5 minutes. Sincerely, I don't like this too much. I would have wanted also here to have some values. This ligament doesn't seem to work very well. The sacrum is not bonded to this big ligament here. So let's just stop it. Yeah, the sacrum is not. Anyway, the FEA stopped by itself. Let's animate just to see where the problems are. You see, here, I didn't bond these three. Okay, and I need to add not only these, but also this. I need to remake the selection. also on the other side. Yeah, here it's correct. We have this one. Only what I have forgot is yeah, I have forgotten to these two. So everything is nice now. What do we have here? The other ones from below, and here is the with the pubic symphysis. All right, perfect. Is are 5 millimeters all right? Maybe we should go for 10. At least with the ligaments here, maybe. Huh? Let's see with 5. So do we have any reply? Maybe in the future. So you are seeing from the start of the stream until now, you are seeing from the very beginning the trials and tribulations of an FEA engineer, of a simulant, of a researcher. So you can either try and learn some of the things, of the procedures, of the methods that I have shown you here, I showcased in the stream, or feel free, if you have similar scenarios, feel free to contact me and hire me and ask for my support to help with your project or your thesis or homework. Of course, that I'm available for cooperation. I can easily understand the fact that the first time when I installed ansys, I think it was in the year 2000, and I can understand that someone who opened ansys 1 or 2 years ago cannot possibly know what I know. He or she do not have the experience that I have, and this is why we need to cooperate and ask for help. And thankfully, you know the right person, which is in front of you, right here, right now. Just feel free to contact me. You have my website. We have the contact page, and we have the email. So I'm just an email away. Or you can wait for, I don't know, 5, 10, 15, 20 years and accumulate the knowledge needed to perform such complex scenarios. I'm talking especially about the biomechanics side, which is very complex. I say this with all my modesty. It's not for beginners. It is very, I would say, interesting and captivating, but it needs a lot of work. And beginners can very easily get stuck. Oh, now it was nice. Look here. Look here. A gradual propagation of the displacement. Yes. Now it was nice. Yeah, let's let it solve for a while. I don't know how much the FEA will work because I have seen it kind of stop by itself. There was a recurring thing that I was doing, ansys biomechanics, where I usually checked what my other colleagues have done with similar scenarios. So let's see what other people have done in ansys workbench regarding biomechanics. I will not say vertical shear, pelvic vertical shear, because of course nobody approached this on YouTube. So hi, the 3 people watching me. Admire your patience. Let's see other people. What have they done in ansys workbench regarding biomechanics? Look, beams, yeah, beams. Adequacy, no. This is a pretty easy hip prosthesis. This is a fused vertebrae, which is not nice to have one. I think it's fused, no? Or yeah, fused vertebrae, which realistic, zero realism. The same femur, taken from the same femur, taken from the same places. The same femur, so nothing. This is the topology. It's so simplified, I'll not say how it is. So, computational biomechanics, look here. Computational biomechanics. This is computational biomechanics. Planting solidifying. This is a nice intention. Oh, it works. So let's see here. I would like to see more bodies. For cushion, 0.01 millimeter is close to 0. So the FEA is almost useless. 0.08 useless. The mesh is too coarse. 4 megapascals, it's almost useless because in reality it's 2 or 3. Look here. Total deformation, when you have total deformation 0, then it's a big no-no. This is why he shows only 20 seconds from the entire simulation, because this simulation is almost 100% unusable and useless. But this person can, of course, evolve. Yes, in time he can evolve, Mr. This is how I have done it, okay, in many years, so everyone can improve in time. This is a knee joint. I will not comment what is here. It's, yeah, this person is in the beginning. Look at the displacement, 2.5 meters, 2,500 millimeters, 2.5 meters. So this says everything. Please evolve, or dear sir, don't show these things at this moment. Look here, 11,000 megapascals. 11,000 megapascals. When steel breaks at, I don't know, 300 megapascals or more. Sporting kinesiolog. You're in a hurry. You're in a hurry to present things. Don't hurry and just do something useful. What is this? What is this? What is this? He fixed only half of the artery. 6,000 megapascals in the artery, where we should have maximum maybe 1 megapascal, maximum 1 megapascal. 6,000 megapascals. Static structure. He fixed what? So he fixed. Look here. He fixed the bottom half of the artery. He applied a force of 30,000 newtons. 30,000 newtons is more than a big car, SUV, or a Hummer or something. And axially, not even radially, to act like a pressure. And of course, this is the geometry that I've seen on GrabCAD, I think. He didn't correct the geometry. The geometry is 0 because it's clear that the stent is fused here with the blood vessel. So it's... What is this? What? It's sad and laughable at the same time. Here, I think the approach is nice, but the geometry is horrific to look at. Come on, look, you can find geometry. Look here, geometry. Geometry, good geometry. Why do you model when you can purchase for $5 you can purchase the entire skeleton? $49. Let's say this is expensive. Okay. So 27. Yeah. $20. But if you 2.5, okay, but not this. It's not possible. And these models are here 15, 20 years ago, so there's nothing new. So, serious, complex, realistic, and immersive results are nowhere to be found on YouTube, except FEA.com. Yeah, this is the conclusion. So let's see what we have obtained. I would have liked to have here the breakage. We can see a start of a breakage here. All right, you know what? All right, let me fix the entire sacrum and let me fix the pubic symphysis, because we'd like to. So nice results. I like them. 70. We begin to have the fracture here in this ligament. And yeah, let me fix here, and clearly we will have the breakage here. Yeah, it's very promising. It's very nice. So my advice for such colleagues, yes, my advice is wait before publishing something, and struggle for days and weeks before publishing something. This is what I'm doing. I have simulations for which I have worked 2, 3, 4 weeks before publishing. What is this? Model simulation. Model simulation is a simulation where you don't prescribe anything. You can even not fix, no force, nothing, absolute. So just throw a bone and solve. So effort, zero effort. My advice is to wait weeks and months before publishing. This is what I'm doing. And also, if you're a researcher or student or whatever, you working in bioengineering in medical fields, you should clearly have access to this model. Yeah? Toyota human model. This is Toyota human model for safety. You should clearly have it. Given by your professor and by the faculty. If not, this model, there is the Hans model from ansys. If I remember correctly, Hans it's called. Yes, Hans. Hans, human body modeling. Yeah. So you have it here. Ask from a professor, ask from a ansys dealer if you're a researcher or student. Yes. Also free Piper models. Look here. This is free. Just go and download. Of course, they are a K file from LS-DYNA, but you can convert K file into STL, then from STL into solid bodies. How? Research and see how can you do it. But you can, because I have done it. Yeah. They exist, but the easiest way is, as I showed you, CG Trader. There is also Turbo Squid. What do you want? You want a human spine, for example. Look here, 49, whatever. You can sort by small prices, free. What do you want? Cheaper than free. Cheaper than free. What do you want? For $4. Look here. A nice looking spine. $4. Yeah. Do you want it free? Go and grab her. if you want it absolutely free. Look. Easy. Do we have a lot of junk and use this stuff? Of course. But look here. Look, sift, sort, open. This is useful. I have used this. Yeah. This is kind of fused together, if I remember correctly. Download, it's free. This is very nice. This is the human anatomy, the entire human anatomy. Almost entire. And it's free. It's free. It stays here since 8 years ago. So there is no excuses in using such models. Such models. There's no excuses because you can find nicer models. Yeah, let's see if I can find knee, for example. The femur that everyone uses. Look here, knee joint model. Look how nice it looks. It's free. What did I say? I said that I will support. Let's make another. Another support. Did I make it or not? What is this? Ah, this is from here. This is. Do I have two? I have two. So I fixed the symphysis. And let me better fix this one. Let's extend the fixation. Selection, limits, apply, save. In order not to make some of the bones rigid, okay? I fixed them all to increase the probability of shear here. So I was look here how nice it looks like. It's here, yeah, here. So I don't want to point to a certain person, or I don't want to attack. Of course, everyone can and will, if they want, they will evolve. So take your time, and you can evolve. And think, you know, you cannot publish 2,500 millimeters. You cannot show something like this. Or, no problem, let's show it, yeah. But, yeah. It's good for, you know, if you hide the Mr. Ahmed Khan, if you hide the legend and the results, it's nice. It's perfect, and you can make some more, no problem. There will always be desperate persons. Yeah. Ansys abacus. Abacus without Q. And there is no abacus, of course. And if this is a stand, then plague instead of pluck. Plague. God, why? Why showing something like this? Why? So nice. So nice. Do we have something more? Oh, yes. I think it's something kind of similar, maybe a competition for anybody kinematic model, you know? Here the model is fixed here on the rib cage. Yeah, so nice. So nice. So there is no excuse not to have a good geometry, except for next things. So, for example, if you want a heart, then yes, it took me years to find a good heart. Look, for example, what hearts can you find on GovCAD? This is a heart. Yeah, so instead, if you dig very deep, you can find in the end, they have this fetish of showing only half the heart in section, yeah, and you hardly can find the full heart. And a full heart, if you find it, halves, let's say if you find it, it has only textures. and it's not usable, so yeah. It took me so much time to make this model work. I'm not talking about the CFD by itself, which is not very hard if it's done in ansys discovery, but to have a human heart with the proper valves. Here there is a valve, for example. Yeah. It took me so much time, so it was something done 4 years ago. It's a beginning. It's not the top of simulation, but it's a start for something. And to find such a usable, reliable, hard 3D model, it takes so much time. So much time. So let's see, ladies and gentlemen, what we have obtained. So we will clearly have breakage here. Only what I don't understand is here why we don't have breakage. So let's increase the force here. At a certain moment, we have known of forces around 45,000 newtons, so we can exaggerate, no problem. Any comments? Chat disconnected. Okay. So we're closing. We're approaching 4 hours. Let's give some results because it's time, you know. So let's assess again what we had here, 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 here. All right, so we have the force here. Okay. As I said, maybe make it 40,000. And what we wanted to do is decrease a little the geometrical strain limit, maybe towards 0.35 in order to ensure a realistic fracture of the bone. think I need to leave a contact between the sacrum and this. Let's assign a contact. Otherwise, they will interfere. This will fly away and maybe enter the sacrum. Because until now, I didn't leave an interaction between the bone, except femur and we have it here, here also. But I don't have between this and this. So let's leave it frictionless between this, this, and this. At this moment, due to this high load and shock to be transmitted, it can be that such contact, such impact will occur between this bone and this bone. It can happen. Of course, not on this side, because this is fixed, this is fixed. Nothing much will happen here, but on the right side, we need to have this contact. Because if we leave this fly away, yeah, just interfere here, then yeah, it's not, let's say, realistic. Yeah, let's look for biomechanics FEA, but in other software. Because ansys is pretty poor. Pretty nice. I would have liked to have more in this joint, but yeah, it's a nice, nice simulation. This is biomechanics. Finite element models, zebrafish. What is this? Where is the finite element modeling? So in front of the chest there is a plate, and it looks like LS-Dyna here. Just some slides. Plate, but nothing more. Which things anybody can show this geometry. Just asking, is it an assembly or single part? It looks like an assembly. It has the cutouts. What is this? It's the transition of the slides. What is FEA Bio? So 1 hour and 23 minutes to arrange 2 spheres. One hour and a half to arrange some spheres, and they are not arranged. They are not properly aligned. Yeah, so it's almost nothing, almost zero. 0.02 millimeters. What? 0.02 millimeters scaled with 1 million. Why? What is this? One part. This 3D model is also on GrabCAD. Oh, a compilation of the mastership of the best work. Yeah, but he's everywhere. It doesn't matter what you publish. Just make it 100 times. How do I force it to break? Oh, it looks so nice. Yeah, there is breaking almost here and maybe somewhere here. Here there is a tendency. We have breakage. Yeah, it looks pretty nice. It's not perfect, but the tendency is very good. Here we already have breakage, and I would have liked to have breakage here too. What can I do at this moment? Let's run another one, and that's all. I will decrease the geometric constraint limit. I will decrease it to, I don't know, 0.2 to facilitate the fracture. Yeah, so nowadays we have everything if we want, if we search for it. What did I say? That I will go here and make it, I don't know, 0.22. I don't know if it's correct that I fixed here. I don't know how. I think because I fixed here, it. Let's suppress a little this fixation. Maybe I took the possibility for fracture here. Maybe. Let's see. So I wanted to see the leg now. the dummy. The Tom's model is more alive than the people. The people are frozen. Oh, pregnant woman. Wow. Oh. You know what? Let's leave it like this, even though it could be better. We have this here. Ansys stopped. Yeah, it just stopped. Let's make it here, I don't know, something like this. And we have this breakage here. We can have this, let's unsuppress just for a second. Let's unsuppress here. Let's keep this fixation and see what will occur. We already have achieved this structure. Yeah, let's see. Yeah, this looks nice. This is easy to make it, so drop test. No contacts required. No joints assigned, no nothing. Yeah, it's for fun, you know. It was published on Halloween, I think, and yeah, it's nice to see. With the comical underline, boo hoo hoo, and so on. So nice. Yeah, so nice. So, an extensive presentation of Hans. They go and present what was in the market at that time, 2 years ago. Viva, Tooms, Piper, whatever, and then they introduced the Hans model. Okay. You know, there is this trick. Let me show to you if you don't know it. You can show to other people. Selecting here, instead of geometry, kept user surfaces, and it would remove the red areas. It will look like a breakage. Look here, yeah? It looks like a breakage. Kept user surfaces. It removes what's, for example, what's between the top and the second values. The top and the second value, yes? If you modify here, I don't know, maybe if you make it lower, you have more removal of tissue, let's say. If you go towards 100, you have less removal, you know? This is a kind of workaround regarding the breakage for people who cannot achieve breakage, let's say, or mesh erosion. It stopped. Yeah. Because why not? thinking, what is the proper fixation of this side? You know what? Let's fix something like here, something like this, this. Ah, the inside faces. This is a comical title here. I don't know if you can see it. I hope you can see it. Yeah, very nice. So, ooh, we already have the breakage here, and do we dare to have here high stress? Oh yes, oh yes. But it does not lead to breakage at this moment. Yeah, we will leave it like this. And nevertheless, at this moment, ansys doesn't go further than 50%. So let's be satisfied with what we have here. We have breakage here, and lot of stress here, which will lead to breakage. So, ladies and gentlemen, if there are no further questions on live chat, and I see there are, I will leave you here, and yes, good luck in your future. Biomechanical, FEA, ansys simulations. All the best from expertfea.com. Bye-bye.